Hello, everyone. Welcome. Welcome to this session called Building Advanced Agentic Apps with PostgreSQL and on Azure. I'm Maxim Lukiyanov. I'm Product Management Lead on GenAI team on Azure Postgres. And together with me, I have Abe.
Hey, everyone. My name is Abe. I'm a product manager on the Azure AI team working on agents and AI.
Great. So as you have heard from the keynotes yesterday and today, agentic world is upon us, right? But from the developer perspective, what benefits do we get from this agentic architecture, right? From the practical perspective, what does it give us to move from the prior architectures? What's the benefits? So in this session, we are going to answer this question. We'll start with describing benefits of agentic architectures from the practical developer perspective, and we'll compare 3 frameworks. And then we'll talk about how you can build a better agent, how we can improve agents to be smarter and faster. So let's dive right in. Maybe. OK, great. So we'll start from the 4 key benefits of agentic architectures: flexibility, orchestration, memory, and self-correction. And then we'll expand to describe other capabilities that agentic frameworks provide as well. But these are the core 4, and we'll start with the flexibility and orchestration. So let's start from some basics. Let's talk about architecture of the single agent. And many of you have probably heard about it already, but it always helps kind of to get everyone on the same page. So if you look at an agent, it has 2 capabilities. First, it can use LLM to process requests from users. And second, it can use tools. And the tools can be information retrieval tool, for example, from Postgres, or it can be any other tool producing information or taking action. If you take this single agent and connect it with other agents, we get multi-agent system with a great flexibility. This is an example of agentic network that processes, that generates a product page customized for the user preferences, something that we'll see in a demo in a few minutes. As you can see here, we can give each agent different capabilities. So each agent has its own LLM, right, to focus on and process its task. And it also has a set of tools appropriate for the task. And we have a flexibility to give this agent appropriate tools. And with a dynamic routing of the requests across these agents, we get great degree of flexibility of this architecture. Compare it to the rigid retrieval augmented generation architecture from before. The information flow here was fixed. We would always call a vector search before we augment the prompt to the LLM, and then we'll process this request with the LLM, right? So this information flow is fixed, and it limited what our AI systems can do and how they can interact with users. Of course, even before agents have arrived, we had various extensions to this RAG framework, right? There were query rewriting capabilities before you do vector search. So all kinds of extensions were introduced. And you can, from that point of view, you can think about agentic architectures as kind of a generalization or next step on this natural evolution of the architectures of AI systems. So let's jump into a demo to demonstrate one of the benefits, these 2 benefits from the agentic architecture. So what we have here is an agentic shop. It's actually a fully fleshed out solution accelerator that we have built and published today. I'll share the link to the wrapper with you at the end of this session. So that basically builds this multi-agent system to reimagine kind of a shopping experience, right? So what we can do in this agent, first, course, we can search for products, right? So let's do the simple search for products. we get some results expected, right? But in this agent flow, we can see how behind the scenes it was implemented, what kind of agent flow it triggered, right? So here we can see that, let's see. Okay. Here we can see that our command routing agent spent roughly 200 milliseconds to decide that, hey, in order to fulfill this user request, it needs to call a tool search, right? And it ignored these two other tools that is available to that agent. So that's kind of a first glimpse of the flexibility where our agent can encompass all functionality of the app, right? And do the right thing dependent on the user request. So let's take a look at the product itself. Looks like it corresponds to our search query for some good headphones with bass, right? So that looks like a correct result. Some details of the product. So let's see how this personalized section was generated, right, by the agent. So again, agentic flow. Let's take a closer look. So we can see that planning agent this time, again, spent a little bit of time to determine that it needs to call product personalization agent and inventory agent, right, to get some inventory data. But it skipped review agent because it decided that it doesn't need to do that, right? And then these two agents run in parallel, right, and produced result using presentation agent. So let's take a look at the planning agent. Why did it decide to do things like that, right? So here we can see all of the context that planning agent used. It used preferences of the user, right, that were extracted during the lifetime of user interaction with the service, right, here. It has context of the queries that user created. And it decided, hey, these two agents needs to be called, right? So the output of the agent itself is just, hey, this is the next two agents that needs to be called. And it provides, if you look at the product personalization agent, it provides its reasoning, like what it also decided to highlight for the user based on the preferences, on the history of requests that user made. So now, within the same application, we can make a different request, right? So in this personalized section, I would like to see some summary of reviews, right? So I don't need to go down there and read these reviews. I want to customize the UI of my shopping experience. So let's ask our agentic shop to do that. So now, as you can see, our agent was able to determine the intent of our request and doing personalization step, right? It generates a new personalized section for us. So let's give it a moment. Let's see. So now it has a review summary added to our page, generated summary from the reviews, right, and customized the UI. So let's look what happened in our agentic flow. So now we can see that review agent was called to fulfill this request, right? And inventory agent was skipped because we already retrieved the inventory information. And in our personalization agent, right? Let's switch to product personalization agent. We can see that it had a context, planning agent, sorry. And in our planning agent, we can see that the planning agent had the context about the user request, right? And it made the decision to call these two subsequent agents. So that's kind of illustration of how you can build an agent, right, that encompasses end-to-end experience of your app, right? And it kind of can do all of the functionalities that you would like to make available to the users in a very composable, dynamic manner. So let's compare how this kind of capability, right, of building dynamic systems with flexible orchestration implemented and provided by different frameworks. But there are many agentic frameworks out there, right? AutoGen is experimental. Crew AI and small agents is very strong startups, but they're still gaining kind of adoption. Pydantic AI is a great, very new framework, very promising, but has even less adoption. So what we did, we picked these top 3 frameworks as the frameworks with the highest adoption, right? And we compared their agentic capabilities between them. But before we jump into the screen, I wanted to ask you a question. As an application developer or database administrator, what kind of preference for agentic frameworks you might have already? So raise your hand if you're a Semantic Kernel preference. Roughly 20, 15 people. LangGraph or LangChain? Oh, we have a tie. Almost the same number. And anybody LlamaIndex? There are a few people with LlamaIndex preference. Okay, that's unexpected results. Thank you for sharing that. But if you look at this chart, you can see that in terms of flexibility of agentic architectures, that's basic property you get from all of the agentic frameworks. So no matter which one you pick, you can build this dynamic systems with the ability to orchestrate requests. If you look from bottom up, in terms of ease of use, LlamaIndex offers the simplest APIs. They provide a powerful dynamic workflow capability that you can use to build upon and build your own kind of implementation of certain specific behaviors in your application. For example, while building this application, we actually build it using LlamaIndex to make sure that we understand that framework well. And we built the multi-agent and agentic graph capabilities on top of this dynamic workflow, which was fairly simple to build. But other frameworks take a completely different approach to orchestration. LangGraph provides kind of a full first-class support for these agentic graphs, but it makes it very hard to use because it provides very rich functionality, but you have to learn all of those concepts, learn how to build these agentic graphs before you can start to be effective at it. And Semantic Kernel is somewhere in between. It is very feature-rich as well, but it also offers dynamic routing with the planners and skills. So it is a little bit simpler to use, but it's still as powerful as a LangGraph. So that's kind of the discussion of the top 2 elements, the flexibility and orchestration. And with that, let me pass over to Abe to talk about the next thing.
Thank you, Maxim. Hey, everyone. So today I'm going to talk about 2 other pillars in this architecture. First being memory, and the second being self-correction. When we talk about memory, memory is pretty self-explanatory, but adding memory to your agent helps it learn from past interactions and also helps it improve kind of the user experience and how it interacts with future questions from your users. The second one is self-correction. This is pretty important in like an enterprise context because what it can do is you can have other agents correcting an agent's answer. So enough of me talking, let me show you a demo of how this works and so everyone can kind of understand this a lot better. So right now, I'm in the agentic shop. Maxim just showed you. So you can see it's already created a user summary. I'm a different user, and I'm going to quickly show you the graph, similar graph to what Maxim was showing. You can see here that I have a production personalization agent, and the agent knows my preferences about, like, I like things that are premium, I like durable products, and I prefer ease of use. You'd see that in the summary, it kind of talks about those kind of things, ease of use, so on and so forth. So if I'm a user and I want to make sure that this memory gets stored in the agent, what I can do is I can just say something like always show memory or always show summary of the review. So what would happen is the agent will save this into its long-term memory. So every time I create or view a product, it would always show me the reviews because I told it to. So let me show you what that looks like. So if I go back to the shop, and all of this is being dynamically created by the agent. So if I go back to the shop and I click any other product, what you'd see is when it loads my personalization section, it would remember I said always load reviews. So when Maxim first started, you noticed there were no reviews. He told the agent to add reviews. Now I'm telling him one step further. Every time you create a summarization for me, always show reviews. So you can see here, this review is personalized for me. because the agent has memory of my user preferences. One, my preferences, I always want to show reviews. So you can see here, it shows the reviews. It talks about durability, design, and things along those lines, performance. So you can see right here, if we go back to your personalization agent, you can see it saved what I told it before, right? I said always show reviews, but it saved it in a way that the agent can understand. So moving forward, if I were to search for any product or do anything else in this application, the agent will remember my user preferences. So now we understand how memory works. Let's go ahead and let me show you self-correction. So what I'm going to do is I'm just going to turn on self-correction, and we're kind of going to show you how self-correction works. So basically, internally, we have some review IDs, and we don't want the agent showing those IDs. So as it's loading, I'm going to show you how the team of agents work together to solve this problem. So now that's loaded, I'm going to go to that same graph, or the flow, and you're going to see it's a little bit bigger than before. So I'm going to zoom right in. Because I talked about self-correction, what happens is it invokes an evaluation agent. So you can see here, I had a review agent that created the summary of the review. It went through evaluation. Clearly something went wrong. The evaluation told the review agent to do it again, and then got evaluated again and then got the right answer. So let's dive into what happened. So if I find this evaluation agent, so the first evaluation agent, it saw the response from the review agent, and it saw these two IDs, review ID 101 and review ID 102. And it says retrigger because 101 and 102 actually contain internal database IDs. So what's happening is this evaluation agent is stopping the response from the review agent before it goes out, so it doesn't feed your customer the wrong information. So let me look at review agent 2. Basically, the evaluation agent told the review agent, hey, this was your output from before. Can you not have this error? So basically, you caused this error with the internal IDs. Can you redo it with those same preferences? And the review agent actually has a new response without using those IDs. And then you can see the reasoning here. And then the second evaluation agent checks that work again, and you see, OK, everything works. So hopefully that kind of gave you a very practical summarization of how agents work in terms of memory and in terms of self-correction. So I'm going to flip back to the slides. OK, where's my thing? All right, so going back to the discussion Maxim started about the three major frameworks. So what I'm showing here is, again, a chart of the three major frameworks, and all of them are very feature-rich. In terms of memory and self-correction, I would say Semantic Kernel and LangChain apply these just right out the box. If you're using something like LlamaIndex, you have to just work on implementing that yourself. We built that application with LlamaIndex, actually, and built a lot of this extra features by ourselves. But these other two frameworks, if you're just starting, offer those out the box. For me, what I'll recommend is three things. If you're building an enterprise-ready solution, it makes a lot of sense to look at Semantic Kernel, mainly because Semantic Kernel has a lot of integrations with Microsoft-specific products, again, developed at Microsoft. So a lot of Microsoft-specific enterprise tools work right out the box with Semantic Kernel. If you're looking to build something super complex, maybe a super complex agentic workflow, maybe look into LangGraph, because LangGraph has good representations with the Graph UI, so you can see exactly what's happening. And also, LangGraph integrates with a lot of open source and startup APIs, because LangGraph or LangChain and LangGraph are one of the most popular open source chains, graph creation things out there. And lastly, if you're looking to build maybe a knowledge-specific agent, LlamaIndex is a really good choice, because LlamaIndex has a lot of inbuilt retrieval technology that all these other frameworks don't have out the box. So it really depends on what you're trying to do, but I want to give you guys a practical understanding of the right choice to pick when you're making these choices. So now we've talked about the architecture, the frameworks to use. Let's talk about building these smarter and faster agents on Postgres specifically. First, I just want to touch on the rich ecosystem of Postgres itself. The reason why Postgres is pretty popular in building agent space is because Postgres actually offers a very extensive ecosystem of extensions. So things like AI integrations just inside Postgres. We've talked about the semantic operators. We'll show you a demo of that later on stage. Vector search is directly in Postgres. Graph is in Postgres. You can have geospatial data in Postgres. Also, the great part with this ecosystem as well, it's very vibrant community, and they have extensive plugins and support for all those frameworks I talked about. So the 7 frameworks Maxim mentioned, they all support Postgres. So let's say, hey, whatever you're using Postgres and you're building these agents, you might run into these 2 big problems. So when we talk to customers, these are the 2 biggest problems they run into. First being scale, and the second being accuracy. Scale being when you hit over 1 million vectors, you might not think that's going to happen quickly, but with all these agents being built, your database might hit 1 million vectors faster than you think. And the second thing is accuracy. So I'm going to dive in how we solve these problems. The first one is, how do we solve the scale problem with our vector index on Postgres? So today, in the market, if you're using Postgres, there are 2 major vector indexes offered. One being IVF flat, and the second being HNSW. With IVF flat, it actually builds a cluster, and it's super memory, builds a k-means cluster, and it's super memory efficient for searching. But the problem with IVF flat is anytime you add new information in, you have to reindex. So that could be a problem if you're in production. If you're using HNSW, it's super great, very fast algorithm. It's actually built in a bunch of layers. So what happens is if it was able to find the node you're searching for on the first layer, you get really fast results. The downside with this is when you do build the graph is very heavy. So the graph requires a lot of memory. So as you scale up even more, you need a lot more RAM to run that efficiently. So that's why at Microsoft, we're actually we GA'd yesterday, DiskANN. What DiskANN is the Microsoft research-backed vector indexing algorithm that gives you the best of both worlds. It allows you to scale and build these high-scale AI agents for your knowledge bases. So when we tested DiskANN internally, we saw DiskANN perform 10 times faster than an algorithm like HNSW. It was 4 times lower cost because of the compression, and also 32x less memory being used. So how exactly did we get those results? The main algorithm here used in DiskANN for these results is something called product quantization. What product quantization is able to do, it's able to take all your large vectors you have, compress them down, and save them in memory. So what happens is when you do the first pass of vector search, you get that same kind of speed you get from a graph because everything was compressed down and now fits in memory. But you also get a lot of efficiency because the I/O reads that happen with going back to your storage to get more accurate vectors to give you the right answer are very, very minimal with DiskANN. So unlike other compression algorithms, you get the speed of compression, but we also get an accuracy as well because we retrieve some of the full high-quality vectors from your storage and gives you the correct answers back. So enough of me talking again. Let me kind of run a video of how exactly this works super practically. So what I have set up here is I have one database that's indexed with DiskANN. It's a 230 gig database. DiskANN compresses that down to only 10 gigs, the index. Another database compressed with HNSW, and you can see HNSW builds another vector. And the vector graph HNSW builds is 316 gigs. So you can see how this memory usage explodes if you're using HNSW. So next, I'm going to show you what that looks like in Azure. So let's say I have a machine on Azure. Getting the 2 database machines, one for DiskANN, it's running on 16 gigs RAM, and another that has HNSW, also running on 16 gigs RAM. And I'll show you how these 2 perform on a sample data set. So here I have a sample data set of 35 million rows of Wikipedia. I'm going to ask a super simple question. So let's see how HNSW performs versus our new DiskANN. So I'm going to quickly run that. So you can see I selected HNSW. I'm going to ask a super simple question. How does artificial intelligence work? I'm sure everybody wants to know. So I'm going ahead to search that and stinking some more. And it took around 5 seconds, mainly because the graph actually didn't fit in memory. So I had to do a lot of I/O reads to disk to give you the right answer. So we're going to do the exact same search in DiskANN, and boom, pretty quickly, within half a second, you got the answers back. The main reason why, as I explained, with product quantization, we're able to bring all the full vector and fit it into that 16 gigs of memory and get you back results a lot faster. So as you can see, super practically, we're getting 5x improvement on your vector search. So practically, what does that look like as you start paying for your storage and things like that? As you increase your capability of your agents and you add more data to your agents, we see 4x lower costs using DiskANN as you scale up, mainly because as you increase the amount of vectors you're using, you're going to need more RAM, you're going to need more storage, and the costs are going to start going up and up if you're using HNSW, and if you're using DiskANN, the costs go down a little bit less. Now, to talk about solving the second problem, I'm going to hand it back to Maxim.
Thank you, Abe. Great. So let's talk about the second problem, improving accuracy of your agents, right? It's a very common problem where for any app that reach kind of beyond the prototype stage, it becomes increasingly important to make sure that this generative AI app generates reliable or trustworthy responses, right? So how do we do that? So there are many techniques, and today I'm excited to announce a public preview of new techniques that helps tremendously improve accuracy of your generative AI apps and agents, semantic operators. Semantic operators leverage LLMs in your database to bring semantic understanding of your operational data. So they use, unlike vector search that allows you to search for individual items in your database, right, based on the semantic similarity, semantic operators allows you to detect relationships between the items and bring next level of intelligence to your apps. We are announcing 4 new semantic operators: generate, is true, extract, and rank. Generate is the most, sorry, go ahead. Yeah, we have fast slides, yes. Generate is the most common operator out of all of them. So you can basically emulate most of the other operators using generate except rank. It basically allows you to do ChatGPT-style generations in your database. It allows you to use any AI model from AI Foundry. Is true is a natural language predicate evaluation operator. You can use it for filters and joins. Everyone took a picture? And extract is probably the most transformative operators of them all. It allows you to extract knowledge from your data. It allows you to basically look for the entities and relationships between entities, extract them, and convert them into structured data, and then enable your database and application reason about this data, bringing this next level of intelligence to your app. And finally, rank is a highly accurate semantic re-ranker operator that you can use to improve accuracy of your vector search. So this operator supports 2 types of large language models: the cross-encoder, which is a very fast re-ranker model, and LLMs, which are very highly accurate re-rankers. So next in our list of kind of techniques to improve accuracy of the application is another powerful technique, GraphRAG. So let's talk about that, and then we'll demo both semantic operators and GraphRAG working together. So what is GraphRAG? So the idea of the GraphRAG is enabling your agent or GenAI application to perform graph processing on your knowledge graphs. And that allows them to unlock kind of a next level of intelligence and ability to understand relationships in your data and bring more relevant responses. From the agent point of view, graph queries is just another tool on the information retrieval toolbox. But when we talk to our customers, the first question that comes up when you start talking about knowledge graphs and GraphRAG is, hey, how do I build this graph in the first place, right? And how do I consume it then? So to help with that, in large degree to help with that, we actually introduce the semantic operators. Semantic operators make it extremely easy for you to extract entities and relationships in your data and convert it into a graph representation, then store this graph, and enable your applications to start reasoning about these graphs using graph queries. In Azure Postgres, we support graph storage support natively through Apache Edge extension. And Apache H extension provides support for industry standard at this point, graph query language called OpenCipher. So that kind of triplet of technologies, semantic operators plus Apache H or graph storage, graph database, and OpenCipher graph query language enables you to basically implement this next generation GraphRAG techniques in Azure Postgres. In addition to that, we also support the second option of how you can build this GraphRAG. So in collaboration with Microsoft Research, they've built this GraphRAG library, Microsoft GraphRAG, which you probably heard about in the keynote just before. So there, GraphRAG library was applied to code to extract relationships between code elements. But you can apply the same GraphRAG library to extract relationships from any data. So GraphRAG library, the benefit of it is that it completely automates this graph extraction and consumption process. It basically gives you functions to do that. So you don't need to even reason about what kind of graph I need. It will build graph for you from your unstructured data directly. And as you can see, many of the things in our database or GraphRAG support are dependent on the Apache H. So I'm excited to announce that Apache H on Azure Postgres is now GA. I need to work on my pitch. The people don't get a clue. OK, so Apache H is ready for production workload, so you can start building these GraphRAG systems and apply them to real projects. And before we jump to a demo, another reference. So Microsoft GraphRAG technique, right, that I mentioned is another way of building your graphs, very productive. So here's a couple of links. We have built another solution accelerator that illustrates how you can apply it on top of Apache Postgres to build graphs automatically from your data. We also had an Ignite session half a year before describing that. So I'm recommending going to those resources if you'd like to learn more about using Microsoft GraphRAG. But in this session, we'll focus about using semantic rankers, semantic operators with Apache H. And before we jump to a demo, yet another announcement. In the demo, you'll see new Postgres extension for Visual Studio Code. That's another public preview that we made available yesterday. So we are very excited about it. We put a lot of effort into making it high quality and delightful. So this is something I'm really looking forward to seeing how anybody uses it. It works with any Postgres database, on-premises, in the cloud. But of course, it works even better on Azure because it supports Azure-specific features as well. OK. Oh. That's how you do it. OK. Great. So now we can jump into a demo. So let's jump into a demo. So first, let's go back to our agentic shop and illustrate one more sophisticated query that traditional vector search is not able to fulfill because this question, this request, implies understanding of the relationship between things, right? So we are asking for headphones with positive reviews about noise cancellation, right? Not just good headphones with good reviews, right? But specifically about the evidence from the reviews about a particular feature, noise cancellation. So that implies a semantic relationship between noise cancellation feature and the body of the feedback in the review. So in our application, we have implemented this. So it's able to fulfill this query. So if you look at the agentic flow, you can see that now it used search with sentiment tool, right? A separate tool. It detected that, hey, it involves reviews. So it did the smart search instead of a regular vector search. And to double check that everything went as expected, let's take a look at this product that it returned and check its reviews. So let's search by noise. And you can see, hopefully, it's stellar. So there is evidence that noise cancellation is actually great, right, in the reviews. So this is what our application was able to connect. It was able to connect the dots between evidence in the reviews with the user query. So now let's switch to a Visual Studio Code and talk about how we made this happen in the app. So first, let me introduce you to semantic operators, right? So this is the generate semantic operator. It simply generates data for you. In this case, I'm asking it to generate descriptions for my product, right? So it's able to use LLM to generate some data for me, very useful for data generation, right? For test data generation. Next, let's jump into a semantic ranker. So first, this is how a regular vector search looks like in Postgres, right? So we are searching for some headphones, right? And what we get back is some results that are a little bit confusing, right? Like this playtime. So I'm asking for headphones with high playtime, but the headphones are returned in kind of random order based on the playtime, right? So I know that we can do better. So to improve results, I'll use semantic ranker. So this is how the query looks like. So let me close that for a second and execute it. So first, we start with a regular vector search, right, here. But then we re-rank results using rank operator, right? And that allows us, hopefully, oh, I didn't click execute, sorry, 1 second. Let's execute this query again. Yeah. Oh, what happened? Some error happened, okay. One more try. Okay, so now if you look at the results, you can see that the playtime is ordered correctly, right? And our semantic ranker was able to prioritize the headphones with the highest playtime. Live demos are always challenging. So that's semantic ranker. And now we can switch to this more sophisticated kind of knowledge extraction operators. So this query, oops, something happened again. OK, that works. This query allows us to do semantic join, right? So we take product features, we join it with reviews, right? So we get permutation of all of the combinations. And then we say, hey, only return combinations that actually have this condition to be true, right? Where the review actually mentions the feature in its body. And using semantic operator like this, we can easily formulate this query and perform the semantic join on unstructured data. So now we can build on top of that query and use extract feature, right? So this semantic join is the same, but for each extracted pair, now we are extracting a sentiment, right? We say, hey, what is the sentiment about this specific feature in this review, right? And we are able even to define what is the meaning of the sentiment, all of these details here. And in the results, we are able to extract that, hey, for this review, sound quality was good, but in that one, sound quality was meh, right? So that allows us to extract this knowledge about connections between reviews and features. And in our app, what we did, in order to make our search experience actually very fast, we did a data pre-processing. So we pre-extracted everything, right? So this is a little bit of snippet of code from the app that shows that, hey, as part of the data migration script, we are doing extraction. We won't dive deep into this, but this is just to illustrate that you can basically in your ETL pipeline, right? You can pre-extract easily everything. Then let's move to the next step and use that extracted information to create a graph that represents this data in kind of a more easily consumable form for your intelligent system. So this is a Cypher query. I don't know if you're familiar with that. But here we're using this graph query language to create nodes in our graph that represent relationships between sentiment about the features and the features themselves. To help you understand it, I have this nice little visualization in my Python notebook that illustrates the structure of the graph that we have built in Postgres, right? So we have products, we have reviews, And now we have created these feature nodes and connected each review to multiple feature nodes that they mentioned, right? And extracted sentiment. So that graph representation is a knowledge graph about our reviews and their relationships to features. And now using this knowledge graph, so this is how our app does it. So this is a query, the graph query that traverses this graph and counts like, hey, how many positive reviews do I have about this feature for this product, right? So this is how this query looks like. It's a little bit complicated, so I simplified it here to the degree that I could simplify it. But we can run this query, right? And we can see the results. For our headphones, for the questions that we had, headphones, right? So we wanted to know about the noise feature, and we wanted to count the positive reviews. So we did that, and we were able to prioritize headphones with the most number of positive reviews about this specific aspect. So this is, in a nutshell, how things work. Right? And I think we're good on time. So with that, let's switch back to the presentation. And we can talk about a little bit about the resources, and then we can open up for the Q&A. So in terms of resources, as I mentioned, the application itself, right, the agentic shop, you can find it on this AKAMS agentic shop. So that's the primary resource that we talked about. And you can see all of the code, all of the graph queries, and how to perform instructions of the relationships. And you can apply it to your own use case. We also have a blog that describes how to use agents with Postgres, right, using, I believe, LangChain, right?
Yeah.
This agents blog. Also, 3 other solution accelerators that talk about GraphRAG and other aspects of development of agentic systems on top of Postgres. Nice video to highlight. Please read up about the Azure blog post. And if you're interested in other sessions about Postgres, we have demo session about Visual Studio Code that Joshua here will be presenting, I believe, tomorrow. Please attend that. And a lab where you can kind of give it a try and practice with the GraphRAG. It will still happen tomorrow. One more instance, another one happened yesterday. And in terms of conferences, we attend all of the Postgres conferences, PGConf. So please, if you attend those, come by our booth. And also we have a conference called POSET, it's a virtual conference that Microsoft organizes for open source community of Postgres developers. It will happen in June, very soon. So you can tune in. It's completely free. A lot of good content about Postgres.
Yeah, and if you guys want to see my face again, I'll be up POSET, so you can check it out as well.
Great. So we can open up for any questions you have. Oh. Yeah, go ahead.
So are these semantic operators in the DiskANN part of Postgres itself, or specifically Azure Postgres?
Oh. It is specifically Azure Postgres. So the question was, DiskANN and semantic operators, are they specific to Azure? The answer is yes. We do have a longer-term plan. We still don't have the timelines determined. Open source, both of those projects, but it's still in the works.
So when you're using the semantic operators,
Oh, so the semantic operators, where you're doing an embedding, which LLM is it using to do that embedding? Which model? How do you control that? And then same thing with the the extract and create.
Yeah, great question. So by default, it uses a default model. In this scenario, we used GPT 4.1 for extract operators. And for the embeddings, I believe in this app, we used ADA002. Yeah. But again, through a parameter, it's an optional parameter, you can control which model to actually go to use.
Yeah, and the models are hosted on AI Foundry.
Yeah.
Hello, Microsoft GraphRAG is a little bit expensive when you re-index or when you add data to it. Do you mean to imply here that you've solved the problem by making the re-indexing another layer? Is that what I take?
Unfortunately, no. Like these semantic operators still use LLMs to extract data. So it would be the same story. So it would be pretty expensive if you apply it on large volumes of data. Microsoft Research is looking into this problem. So we are hoping we'll be able to provide some solutions in the future. But right now, yes, LLMs, if you use it for extraction, data extraction, you'd have to like pay for all of those tokens.
Hey, so we've been using pgvector natively, and we also use hybrid search, and we have our very own implementation for it. We've been looking at pgRunga, which is an extension that Postgres now supports. Is that something that will be available on Microsoft for us to do hybrid search?
Abe, do you want to take that?
What was the name?
pgRunga?
Runga?
Yeah.
How do you spell that?
ROONGA.
I haven't heard of that.
I haven't heard either.
Yeah. What does it do?
It just supports hybrid search, so keyword search plus semantic search out of the box.
Okay. Gotcha. Yeah, I mean, like today with pgvector, I mean, you can still do hybrid search. I'm trying to understand, like, is there a specific feature that you like about Runga that you'd want to see on Flex? Yeah,
it just does keyword search out of the box for us, so we don't have to like create those BM25 tables,
got it.
calculate.
Oh, so it supports BM25 as well?
Okay, got it. Yeah, so yeah, for us, in terms of support for BM25, that's something we're looking into for this upcoming quarter. So soon, Flex is going to have BM25 as well as pgvector and DiskANN, so you can use all those extensions together to solve a similar problem. But pgRunga specifically, I'm not sure I don't have it.
Is it open source?
Yeah.
Yeah, we'll look into it. Huh?
Yeah. Oh, okay. Oh, it's on the radio. Okay, cool. Yeah.
Yeah, so maybe we'll actually implement BM25 using pgRunga. Did you have a good experience with it?
Yeah, I think we use Superbase, which supports pgRunga.
Got it.
But as long as we have an out-of-the-box implementation of BM25, we don't really.
Okay.
Yeah.
Yeah, I mean, also speaks to some of the benefits we're talking about Postgres. Like, if this is an extension that people are really looking into, guys on the team as well, so we can help light that up too.
Awesome, thank you.
Yeah, BM25 is coming.
Yeah. Another question. Any other questions? Oh, at the back.
Thank you. This is generally for the textual search only. No, do you support anything for tabular search in which we have numerical data or something?
Can you elaborate? What do you mean tabular data?
So, like, if data is like device IDs and data like this, like what's the usage of those devices, something like that, where we want to see which device used more than X amount of data or something like that.
Yeah, for device ID, so for very unique elements in your data that you search, keyword search usually produces best results. You can also try vector search. But in our benchmarking, this is exactly the use cases where keyword search kind of is superior to vector search. In literally all other use cases, vector search is actually better. But for like very precise device ID kind of search in the large volume of text, I assume, keyword search is much better. Like BM25 variant would be also something to look into. But that assuming that you're searching for these IDs inside of the volume of text, or is it just a column where these IDs are contained? Oh, just a column.
Related to the data basically related to particular device ID we want to search. We want to find information about a device ID or a group of device ID.
Yeah, if it's an exact search, then just a standard B3 index would work best.
Okay.
Cool. I have a question up here.
Today's the first I've ever heard of Apache Age, and I'm curious if you guys did benchmarking. How does Apache Age inside of Postgres compete against other like native graph databases like Neo4j or something like that?
Yeah, that's a great question. We are still in the process of benchmarking. So our benchmarking at the moment provides kind of the guidance for our customers, and we publish that documentation on how to achieve good performance on large graphs. So there are indexing techniques that we documented that you can apply to kind of scale age to large graphs. We still haven't kind of compared it to like Neo4j or other graph databases. I would expect that they will be faster because they have optimizations for native graph storage, and Apache Age works on top of a regular Postgres table store, right? So it's not optimized for graphs. But that's the beauty of it, because then you get all of the benefits of managed database, right, and very low cost of deployment of this graph database. So expect it to be probably slower, but much cheaper. Right?
And just curious, is there a use case you're using Graph for as well?
Yeah, we're just sort of looking into GraphRAG and building these like lexical graphs to link documents in ways that aren't easily uncovered by traditional vector search.
Got it.
Small follow-up question. Are these slides going to be online at all?
I think so, yeah. Build publishes slides, yeah.
Okay.
I don't know when they will be available, maybe today even, or maybe like in a few days.
Cool. Thank you. Very interesting talk. Thanks, guys.
Thank you.
Oh, question up here.
Are there any other semantic operators that are like on your roadmap or?
Good question.
Yeah, it's a great question. So there are many other semantic operators that we might add. We'll go by customer demand. Our current approach is this generate operator. It's actually very powerful. I didn't have time to mention it, but there is one parameter that we provide for the generate optional parameter, JSON schema, which you can specify and force it to produce structured output. If you're familiar with that concept with LLMs, that basically gives you flexibility to do anything you can imagine, right? You can, like for example, our extract operator and this true operator are actually implemented on top of generate. They just provide structured schema of the output, and then they interpret the results as a special type, right, as a native type in Postgres. So you're welcome to build your own kind of little function wrapper around generate and implement basically any semantic operator you might imagine.
So am I to understand, like, there was this whole like new kind of language that you guys built for the semantic operators in conjunction? Why wasn't the approach to just it be a natural language and that the generate then generates the code for where it looks into, instead of like, oh, like equals this and that, like, and you had the pipe bars and stuff? Well, why the new language instead of just using generate?
So the language, are you referring to the graph query?
Yeah.
Yeah, so basically the idea behind semantic operators is you take unstructured data, and using the semantic operators, you convert it into structured data. Mm-hmm. And in this case, we store the structured data in a graph. And then it's just a graph query language that we use, right? All of this cipher, match, all of that stuff, that's just kind of industry aligned around how do you query the structured graphs. This is a language for that. In terms of generating the cipher queries themselves, in the app, we actually use a tool, right, where we have like this very specific graph query implemented. But you can also use natural language to cipher conversion, where you can ask LLM, like, hey, here is my structure of the graph, and here is the user query. Please generate the graph query that answers it, right?
Perfect, yeah.
Yeah, so you can totally do that. And then you will combine all of those LLMs in multiple places.
Yeah. Thank you.
To his point, I think if you use natural language to turn it into queries, I think text to SQL as a concept is still unreliable. So are you going to be confident that the LLM is generating an accurate query. Yeah, exactly.
Yeah, this is excellent point. So NL2SQL is definitely not a solved problem today, right? So you cannot rely on it. And the situation actually is improved with NL2 cipher, NL2 graph queries, because graphs tend to have more regularized structure, and conversion into a graph query is actually more reliable. So you might find higher rate of success with graphs in terms of conversion of natural language into graph queries.
Yeah.
All right. You guys covered Semantic Kernel, LlamaIndex, and LangGraph in the initial part of the session. So are there any plans? Of course, you can't speak on behalf of LangGraph and LlamaIndex, but are there plans to like create wrappers around these queries so that I don't have to like type out all the things and just provide the information that I need to provide?
It's a great question. Actually, our team is working on improving these integrations, right? So the beauty of Postgres is that it's very broadly kind of adopted in the ecosystem. So every agentic framework, every GenAI framework has support for Postgres. And we are working with these frameworks contributing kind of enhancements. So we actually plan to provide some level of support. We're still not clear what it will look like, but we are aiming to provide better support in these frameworks for Azure-specific features.
Yeah, so like today, right? Like if you're using LangChain and Semantic Kernel, you will be able to use Postgres. You can also even inject specific SQL queries, right? I mean, just as a stopgap for now, and use those in whatever framework you're using. But yeah, as Maxim said, we should have that enabled fairly soon. Oh, right here.
I'm curious why you weren't showing anything with Foundry and agent service. I'm curious why you used Semantic Kernel, and given everything we're seeing today, there wasn't any Foundry and agent service.
I mean, do you mean it with the frameworks, or do you mean with the demo?
Well, just with your demo. Like, why did you do Semantic Kernel instead of putting those agents in like Foundry and the agent service?
I can talk to some of this.
Yeah.
So the application you saw itself was actually built with LlamaIndex.
Okay.
So we kind of implement that differently. Semantic Kernel works with Postgres out the box as well, but the agent service also works with Postgres. So we could have picked whichever one.
Yeah, okay.
It works with all of them. I think for this demo, we just picked
Makes sense.
LlamaIndex. Yeah.
Okay.
Yeah, it just budget of time, right?
Yeah.
If you bring in AI Foundry, and then I'm sure there's like probably 30 talks about AI Foundry already, right? Then it would have consumed too much time.
Hey, so you just mentioned that text to cipher or NL to cipher is more reliable, which is surprising to me because I've had the opposite experience. I've had reasonably good luck with text to SQL. Maybe I'm doing it wrong, but I was hoping you could elaborate a little bit more on why text to cipher seems to be more successful.
I guess it depends on the structure of the graph, right? So if you know the ontology of the graph and it's kind of regularized or static, then we had customers that reported kind of success stories with that. Maybe in your case, the structure of the graph is dynamic, or maybe it's just different from the success stories, or maybe your cipher queries are just too complex, right? You can do pretty interesting things with graphs.
Yeah, I think we've been trying to use LLMs to generate some of the ontology, to extract it from the documents to generate an ontology, which is sometimes difficult because it'll give two different names to the same relationship, for example. So that may be why that would make sense.
Yeah. One of the criteria for success is you need to provide the ontology, right? So in our success stories, the ontologies were actually fixed. The customers provided them as a prior knowledge. Yeah, if you're trying to dynamically infer ontology, probably there's like just too many points of failure.
That makes sense. So when you guys are doing stuff like building these graphs in Postgres using your semantic operators and everything, you guys are predefining your ontologies when you're building these graphs, like as a rule, essentially?
As a rule, well, in our use cases, we didn't have dynamic graphs so far. At least they didn't come up, but I wouldn't say it's a rule. We are still exploring this space. So I'm actually open. If you have a dynamic graph example, I would love to hear about it, like maybe after the talk.
Sure. Yeah. Thank you.
Okay, sweet.
Okay, so we are at time. Thank you very much for your questions and for attending the talk.
Cool. Sweet. Thanks, everybody.